In this section, we're going to cover some alkyne reactions and reaction mechanisms. Here is a list of the reactions that alkynes will undergo, and they will undergo reactions that are very similar to that we saw of alkenes. So when we have an alkyne, and this is just going to represent some generic alkyne, what we have is we have a triple bond, which consists of a sigma bond plus 2 pi bonds. And so that electron-rich region of the alkyne can act as a nucleophile. And so if that's going to act as a nucleophile, that means that it's going to use its pi electrons to attack various electrophiles. And so some of these electrophiles we've already seen before. So when we have hydrohalogenation, or HX, that could be an example like HBr. Or halogenation, we'll learn what will happen whether you have one equivalent or two equivalents of a reactant. You'll get different products. That could be an example like Br2. Hydration reaction means actually adding water across the double bond. We have a catalyst that's used, mercury sulfate, and it's ran in acid, which is sulfuric acid. Hydroboration oxidation, that used borane tetrahydrofuran complex. And then in a second step, sodium hydroxide and hydrogen peroxide for the oxidation. Reduction of alkynes, we're not going to do a mechanism here, just a reaction. So H2 hydrogen gas over a catalyst, usually it's like platinum or palladium plated on carbon. That gave us alkanes. And then these two, Lindlar's catalyst or a metal like sodium that's highly reactive in ammonia, we'll learn that either one of these two could give us either E or Z alkenes. So we have a way to control the reduction. We can reduce all the way to alkynes, or we could possibly reduce to a certain stereochemistry of alkenes. Oxidative cleavage, usually ozone with something like dimethyl sulfide, or we saw could be H2S. That is going to cleave the pi bonds and the sigma bonds in our reaction. And then a new class that we'll learn with acetylide anions use a very strong organic base, such as sodium amide, something called a Grignard reagent, or an alkylithium, in order to remove a terminal proton from the end of an alkyne. So in this example, because we have a hydrogen there that's bonded to the triple bond directly, this is called a terminal alkyne. So this is just a quick overview of what we're going to go through together on the next couple slides. When looking at a hydrohalogenation reaction, it's possible to get different products depending upon how many equivalents of the reactant are used. So for example, let's look at a generic alkyne here. We're going to use a terminal alkyne. And if we do this reaction with one equivalent of HBr, what we're going to end up getting in this case is an alkene. So count your carbons of your alkyne, 1, 2, 3, 4. We still want to have 4 carbons in our final product. And in between carbons 1 and 2, there's going to be a double bond present still. But what was added across the double bond is going to be HBr. And on the more substituted side, we saw when we learned alkenes, that's where the bromo group ended up, or the halogen group. And on the least substituted side is where the hydrogen ended up. Now there's still another hydrogen over here because we had one already present due to it being a terminal alkyne. But our products, when we use one equivalent, end up being alkenes, halogenated alkenes. And the other thing we can do is we could say, instead of using one equivalent, we use 2 equivalents of HBr. So an alkyne has 2 degrees of unsaturation. So one equivalent essentially reacts with the first degree of unsaturation. And if we have 2 equivalents, we're reacting with both degrees of unsaturation. In this case, we get an alkane as a product. So we still have 4 carbons, but we end up getting 2 halogen groups on the more substituted side. And so over here on the other side, we would end up with 3 hydrogens. because essentially the addition reaction would be done twice. The first time we're adding to an alkane, the second time in the mechanism you'll see we were adding to an alkene. So it's no different than we've already learned. So why this works is that the addition of a hydrogen halide like HBr to an alkyne, we can have different spots where we isolate, whether we use one equivalent or two equivalents, is that the second addition in the reaction is slower than the first. So we have a slow second step and a fast first step. You'll see that there's a carbocation intermediate, and it can be destabilized by the polar effect of bromine, and this polar effect will be counterbalanced by the resonance stabilization. So the second addition is slower, and we can isolate the product of the first one if we stop after using one equivalent. So we'll look at the mechanism on the next slide, but just know that you have to pay attention when you're dealing with something that has 2 degrees of unsaturation to whether there are 2 equivalents or 1 equivalent listed. So starting off with, we have our alkyne, which we know is going to function as our nucleophile, which is our electron-rich species. And on this page, this shows the mechanism for using the full 2 equivalents of our hydrogen halide, but I'll show you where you would stop in the mechanism if you only used 1 equivalent. So we learned that HBr is a polar molecule, and so that means that the hydrogen side is going to be partially positive, and the halogen side is going to be partially negative. So the hydrogen is going to function as our electrophile that our pi electrons of our nucleophile will attack. So starting with our pi electrons, we're going to attack our hydrogen, and the electrons in the covalent bond stay with the bromine and form bromide anion. And when that happens, you have to count your carbons and rearrange because you're going to still have some pi electrons there. Your alkyne is going to turn into an alkene. So we have 1, 2, 3, 4. And then when you draw your next step, you're going to have 1, 2, 3, 4. So you still want to have the same number of carbons when you move forward. And your triple bond was between carbons 1 and 2, and now your double bond is between carbons 1 and 2. Just like when we had an alkene that we were starting with, we had to decide which side is that hydrogen going to go to. Is it going to go to carbon 1 or is it going to go to carbon 2? And it depends upon the stability of the carbocation. In this case, the carbocation has a special name. It's called a vinyl cation. You might remember the word vinyl meant that it was right on the double bond of an alkene. And so in this case, since our carbocation is sitting right on a double bond, it's considered a vinyl cation. So we had 2 possibilities. We could go to the first vinyl cation or to the second vinyl cation. So it could either be primary if the hydrogen was added to carbon 2, or the vinyl cation could be secondary if hydrogen was added to carbon 1. And so we learned that a secondary cation is going to be more stable than a primary cation. So that's going to dictate what side the hydrogen gets added to. So the hydrogen ends up getting added to the first position, creating the more stable secondary cation, the more stable vinyl cation in this case. And then next what happens is our bromide anion that was formed can attack that vinyl cation. So we're going to have that be our new nucleophile attacking our electrophilic carbocation. And we don't have anything to push after that. It's just a direct attack. We form a bond there. And so this represents down here that new carbon-bromine bond that was formed. Notice the alkene is still intact. And so we added a hydrogen and we added a bromine across our triple bond so far. This is where you would stop if 1 equivalent was used. The reaction would end right here with our alkene. We're going to keep going though now, so we're going to imagine that this is our second equivalent of HBr being used. And then what happens is our alkene does the same thing. It acts as a nucleophile. It attacks the hydrogen. The electrons break and go to the more electronegative bromine. In this case, we form a carbocation. The carbocation is going to go on the more substituted side because that's the more stable carbocation that's formed. And then our bromide anion would attack that carbocation directly, and we would end up with 2 bromo groups coming off the same carbon, or 2 halogen groups. depending upon what the hydrogen halide that you're using in the reaction is. And so this ends up on the most substituted side, which was carbon 2 in this case. Notice that there's 3 protons on carbon 1 because we started with a terminal alkyne. If it was not terminal, then there wouldn't necessarily be 3 protons there, but 2 would have been added due to the mechanism. The mechanism for halogenation of an alkyne is very similar to hydrohalogenation of an alkyne. It's going to depend upon if we use one equivalent or 2 equivalents. If we use one equivalent, we're going to observe alkenes forming. If we use 2 equivalents, we're going to form alkanes. When we form alkenes, you can technically form a mixture of cis and trans, even though it says here only trans is formed. Trans is typically going to be the major alkene product, and cis would be the minor. If you recall back to when we first talked about alkenes, having a trans orientation is more stable due to the fact that the groups are spread out. The bulkier groups are spaced out. They're on opposite faces of that alkene. Whereas when they're cis, they're on the same side, so they're a little bit more sterically hindered. So they both will form to a certain extent, but the trans is going to be the major product that you want to show for sure. And then if you take that alkene and you react it again with another equivalent of your halogen, you're going to end up with a tetra-substituted alkane. So notice there's 2 chloro groups on this side in this example and 2 chloro groups on this side. So this reaction also works using bromine or iodine, so Br2 or I2. You don't have to write the CCl4, that's carbon tetrachloride, that is just representing a solvent. So a lot of times that's just left out, but the reaction does have to be carried out in some sort of medium. So this mechanism should look really similar to the one that we just covered. It essentially follows the same series of steps. So we're starting with our alkyne that has 2 degrees of unsaturation, and it can react either once or twice depending upon how many equivalents of our halogen are used. So in our first step, we have our nucleophilic pi electrons of our alkyne that are going to attack our electrophile. And so you might recall that a halogen that's normally nonpolar, like bromine, can actually develop a partial dipole moment. So it'll have one side that becomes partially positive, one side that becomes partially negative when those electrons shift and move around. That instantaneous dipole can induce a dipole in surrounding molecules, therefore creating weak polarity. So the side that's partially positive would represent our electrophile. That's attacked, and the covalent bond breaks, forming bromide ion, which is very stable. It has 8 valence electrons around it. Now, you have to decide again, what side does the bromine get added to? Remember, we're going to go through the more stable vinyl cation intermediate. So the bromo group is going to end up getting added to the less substituted side so that the vinyl cation can be on the more substituted side. Next, our bromide ion that we form is going to attack that vinyl cation, and we form a new bond. So we have 2 bromo groups that were essentially added across the triple bond. We still have our alkene intact, and this shows over here your cis arrangement and your trans arrangement. So your trans arrangement is the major product, and the cis one would be a minor side product due to it being less stable. So this is where your reaction stops if only one equivalent of Br2 is added. But if we have another equivalent, our second equivalent Br2, now we can continue our reaction. So what we're going to see is our similar reaction to what we had when we just had an alkene. So if we draw this over here, our Br2, what we'll do is we'll have one side that becomes partially positive, the other side that becomes partially negative. Our alkene is going to attack. The covalent bond is going to break. We're going to get a carbocation on the more substituted side. So that means that the bromo group that just got added will be on the least substituted side. So now we have one side that has one bromo group and a carbocation, and the other side has two bromo groups that have been added. Our bromide anion that was booted off will attack that carbocation, and we end up having a tetra-substituted product here. So 2 of the bromos were added in step 1, 2 of the bromos were added in step 2. So we have an alkane that was formed in this case. Let's look at what your products and reactants would look like if you had an internal alkyne instead of in the mechanisms where we did examples using terminal alkynes. So when we had a terminal alkyne, recall one end had a hydrogen bonded. And so it was very clear what side was more substituted and what side was less substituted. With these internal alkynes, they are actually equally substituted. So there is no side that's going to be preferred when they're equally substituted. Your stuff could get added to either side, and so usually what you end up with is a mixture of products. So for example here, if we add one equivalent of Br2 or Cl2 or I2 to an internal alkyne, we said that we were going to get alkenes, and you're going to end up with your trans orientation and your cis orientation. So this is going to be your major, this is going to be your minor product. If you have an internal alkyne and you add 2 equivalents of Br2, we ended up with a tetra-substituted alkyne. And so we had 4 of our halogens that were added across the bonds. First the alkyne, then the alkene in the second step. And so that's still going to be the case. It's just that there's no distinction where it goes first based upon one side being more substituted, one side being less substituted. They're equivalent to each other. You have a carbon here, carbon here, carbon here, carbon here. It doesn't matter that there's 2 carbons coming off here. We're just looking at what's directly bonded to the alkyne. And so once it's not a terminal alkyne anymore, it's equally substituted. It's automatically going to be the same. And lastly, if you have an internal alkyne and you have 2 equivalents of a hydrohalogen being used, such as HBr, you're going to end up with a di-substituted alkane, and you're going to get a mixture of products. You're going to get both the groups being added to this side and both the groups being added to this side. So the large black dot is just showing you where that spot is on the reactants and the products so you can visually keep track. But here you're going to have a mixture. So make sure you're thinking about the mechanism when you're drawing the products and if it's internal versus a terminal alkyne that you start with. In our hydration reaction of alkynes, we're going to actually produce something called a methyl ketone. So ketone is the functional group, and there's a methyl that's on one side next to it. Our reactants are water and sulfuric acid, and there's also a catalyst that's used and usually thrown in the reactants, mercury sulfate. So you might recall that when we did our hydration reaction of alkenes, we had mercury 2 acetate. So it's not the exact same reactant, but in this case, it's just used as a catalyst to help speed up the rate of the reaction. So looking at our generic equation here, count your carbons first. You have a terminal alkyne, so you got 1, 2, 3 carbons. And in your product, there should only be the same amount of carbons. We got 1, 2, 3. So coming off of position 1, notice there's a methyl group here. So that terminal alkyne became a methyl group. And this is why it's referred to as a methyl ketone product that is produced from a hydration reaction. We previously saw that when alkenes underwent hydration reactions, that they formed alcohol products. And when alkynes undergo hydration reactions, they form similar products. So hydration, adding water, we end up forming something known as an enol. An enol is when you have an alcohol bonded to the carbon that still has a double bond here. So the name is a combination of alkene and alcohol, so enol. Now enols, as it's drawn here, are not particularly stable, and so they do a little bit of rearranging in order to make themselves more stable. Because enols are unstable, they will rapidly convert into a ketone in this case, and sometimes they will turn into an aldehyde. But the pair of these two, the enol and the ketone, are called keto-enol tautomers. And so a tetomerization reaction is the steps that show it converting from an enol into its more stable form, which is the keto form. So starting off our mechanism for hydration, we're going to have our nucleophilic alkyne attack our mercury ion catalyst. So in this formula, if you have mercury sulfate, mercury is actually a +2 charge because sulfate is a -2, and so that would represent our positive electrophile. This is a catalyst to help speed up the reaction. The reaction would just occur in acid, but this makes it go a lot faster. So our mercury sulfate will get added to the least substituted side because we're going through the more stable vinyl cation intermediate. And we want to put our cation on the more substituted side. And so we have our alkene still intact. Next, our water comes in and acts as a nucleophile and attacks the positive charge of the vinyl cation. So now we have still this organometallic, so this organometallic mercury sulfate hanging out, but we've also added water to the more substituted side. So we can undergo a proton transfer step where we use another molecule of water because it's amphoteric and it can function as an acid or a base to essentially deprotonate the hydrogen and get rid of the positive formal charge on our water that we've added, just leaving us with an OH group. So notice that your oxygen has a positive formal charge because it has 3 bonds and 1 lone pair of electrons on it. Proton transfers are useful to shuffle around the protons so that you don't have a positive formal charge hanging out on your molecule. So now we have an alcohol here, and our alkene is still intact, notice. We're not going to go through the mechanistic steps of replacing our organometallic mercury sulfate, but know that when you have it in acid, that gets replaced with a proton. So the acid helps essentially remove that mercury sulfate from your intermediate at this step. Next, we're going to go through our tetomerization, because notice what we have now after the mercury sulfate has been replaced with a hydrogen is we have an alkene here, we have a double bond, and we have an alcohol here. And so together those are an enol. And so enols are unstable and they want to rearrange, and so they will undergo tetomerization to be in their more stable keto form in this case. So let's get rid of these arrows so they're not messing up what we're looking at. So what will happen is a molecule of water will grab a proton from the alcohol portion. These electrons in this covalent bond here between hydrogen and oxygen will swing over and form a double bond in between oxygen and carbon. And then at the same time, the pi electrons that are nucleophilic of the alkene go and grab a proton from the acid that is in this reaction mixture. So remember, there's also H2SO4, some strong sulfuric acid in here as well. You might also see H2SO4/H2O due to it being hydration. Some people don't write the water because it's assumed. So once that picks up a proton, this bond will break and those electrons will stay with oxygen, reforming water. So it's just a couple proton shuffles that rearrange this into a ketone. So we formed a new bond in between carbon and oxygen. Now there's a double bond there. And the double bond of the alkene has now been reduced down to a single bond. And we added a hydrogen to the other side. We couldn't add a hydrogen to the left side there where the ketone is because that would have had too many bonds. So this tetomerization is a rearrangement to give a more stable keto form. And notice you can see your methyl ketone product. We have right here a methyl group. So a carbon with 3 hydrogens coming off. And the ketone ended up on the more substituted side that we started with of our terminal alkyne. If it was not terminal, there would be a mixture of products because there would be no distinction between the more substituted side and the least substituted side. The hydroboration oxidation reaction of alkynes is very similar to that of alkenes. It occurs over two steps where first we have our hydroboration, and then in the second step we have our oxidation. So hydroboration occurred using a borane tetrahydrofuran complex. Remember the THF was just there to stabilize the boron of the borane, so THF isn't actually in the reaction. It's a solvent. And then in the second step, we had oxidation, which was done in basic conditions, so basic using sodium hydroxide, but the real oxidizer, the real star of the show, is hydrogen peroxide. Now what's different here at the end is you end up forming an enol. And so the enol undergoes a tetomerization reaction and converts itself into a more stable aldehyde. It's still often referred to as a keto-enol tetomer, but it's an aldehyde because we're going to end up having this being an anti-Markovnikov mechanism where we end up oxidizing the least substituted side versus what we saw for hydration on the previous slide where we oxidized the more substituted side. So going through this mechanism, some parts of it should look really familiar. We're going to have our BH3, our borane, where our boron is actually more electropositive than hydrogen. So we have a partial positive charge on boron and a partial negative charge on hydrogen. The alkyne functions as a nucleophile and attacks the boron in a concerted fashion, meaning all of this happens in concert together. The hydrogen shifts back because it's partially negative and attacks the positive charge that would be forming. The boron ends up on the least substituted side because the other side would be more stable for where the positive charge would be forming before the hydride shifted back and attacked in that concerted step. So what we end up with is we end up with a BH2 group added to the least substituted side, and we end up with a hydrogen group added to the more substituted side. Notice that the alkene is still intact there. We still have a double bond left because we just underwent one attack. Both of these are on the same face of the alkene, so this is syn addition. And then in the second step, all you need to know is that sodium hydroxide and hydrogen peroxide are used to replace the BH2 group with an OH group at the end. You don't have to go through and do all of those steps of the oxidation. Those are usually learned in a higher level organic chemistry class. So that's our anti-Markovnikov oxidation mechanism where we now have an enol. We have a double bond and an alcohol coming off of that double bond directly, and it's on the least substituted side. So the next step is to undergo the tetomerization of our enol. This is just redrawn here, it's the same thing. And so it's going to be a rearrangement similar to what we saw, but what molecules are involved in the rearrangement matters. When we did the hydration reaction, it was in acidic conditions. So water deprotonated as a base, and the alkene picked up a proton from H3O+. Well, now in hydroboration oxidation, our reaction is carried out in basic conditions. So we can't have H3O+ floating around in here. It wouldn't exist in basic conditions. So what deprotonates the hydrogen of the alcohol is hydroxide in this case, because that's a base. And those electrons swing over and form a double bond in between oxygen and carbon. And then the alkene picks up a proton, but it's not going to pick up a proton from H3O+, it's going to pick up a proton from water, because water is an acid or a base, it's amphoteric. Those electrons will swing over and you'll just regenerate more hydroxide ion. So it's important that you think about the conditions of the reaction and what molecules you can actually show when you're doing things like these proton transfers or tetomerizations, because what would actually exist in the reaction at that point. So what we end up with is we oxidized the least substituted side. We formed a double bond there, but it's not a methyl ketone. It's an aldehyde. That's the product that's formed for hydroboration oxidation due to the least substituted side being oxidized. So that hydrogen that you see right here is really just the hydrogen that was there for the terminal alkyne. And that dot would represent this location. So you want to know that with hydration reaction, you get a ketone, a methyl ketone, and with hydroboration oxidation reaction, you get aldehydes. Now, what's a little different is if you end up with an internal alkyne instead of the terminal alkyne that we did our examples with. If you have an internal alkyne, it honestly doesn't matter whether you use a hydration reaction or a hydroboration oxidation reaction because there is no most substituted versus least substituted side. So you end up getting a mixture of products for both of them, and you have to show both of them in this mixture when you're writing out your reactants and products. You're going to oxidize both sides equally. So this side is showing being oxidized where the dot is, and this product is showing the oxidation occurring. We can draw it over here with this dot, this green dot. So there is no distinction between least substituted or more substituted, so there is no distinction between the vinyl cation being more stable or least stable. So that's why you get a mixture of ketone products. You're never going to have an aldehyde product when you have an internal alkyne either, because in order for it to be an aldehyde, it specifically had to oxidize the least substituted side, and you had to have a terminal alkyne. So you're going to get a mixture of ketones when you're dealing with internal alkynes. And it doesn't matter whether you write your hydration reactants over the line or your hydroboration reactants. They will give you the same thing.